Imagine trying to clock something moving so fast it could circle the Earth almost 7.5 times in a single second. For centuries, the very idea of measuring the speed of light seemed an impossible dream, a phenomenon so instantaneous it defied human perception. Yet, through a blend of audacious astronomical observation and ingenious terrestrial experimentation, scientists slowly peeled back the veil on this fundamental constant of the universe. This article delves into the groundbreaking work of Ole Rømer and Hippolyte Fizeau, two brilliant minds whose distinct approaches not only provided the first credible measurements of light's velocity, but also forever changed our understanding of time, distance, and the cosmos itself. Before Ole Rømer, the prevailing belief was that light traveled instantaneously. Rømer, a Danish astronomer, challenged this notion through meticulous observations of Jupiter's moons, specifically Io. While working at the Royal Observatory in Paris, he was tasked with improving the tables for predicting the eclipses of Jupiter's satellites, moments when the moons pass into Jupiter's shadow. These eclipses served as a kind of cosmic clock, crucial for navigation and determining longitude. Rømer's breakthrough came from noticing a curious anomaly in these timings. He observed that the time between successive eclipses of Io was not constant. When Earth was moving away from Jupiter in its orbit, the observed eclipses occurred progressively later than predicted. Conversely, when Earth was moving towards Jupiter, the eclipses happened earlier than expected. The maximum discrepancy he observed was about 22 minutes. Modern calculations put it closer to 16.7 minutes. When Earth moved from a position where it was closest to Jupiter to a position where it was farthest. Rømer correctly hypothesized that this varying delay was due to the finite speed of light. As Earth's distance from Jupiter changed, so did the distance light had to travel from Io to Earth. The delay was simply the additional time light needed to cover the extra distance. To estimate the speed of light, Rømer needed two key pieces of information: the total time delay, observed over a significant change in Earth-Jupiter distance. The distance corresponding to that delay. Rømer used the diameter of Earth's orbit around the Sun as this distance. Using his observed 22-minute delay and an estimated diameter for Earth's orbit, Rømer calculated a speed of light of approximately 220,000 kilometers per second. While this value was about 25% lower than the currently accepted value, due to inaccuracies in the known astronomical distances of his time, his method was revolutionary. It provided the first empirical evidence that light has a finite speed, shaking the foundations of instantaneous light travel and paving the way for future terrestrial experiments. Rømer's work was a triumph of astronomical observation and logical deduction, proving that even the most seemingly instantaneous phenomena have a measurable temporal component. While Rømer's method relied on vast cosmic distances and astronomical observations, the 19th century saw a desire for laboratory-based terrestrial measurements of the speed of light. Armand Hippolyte Louis Fizeau, a French physicist, was the first to successfully achieve this in 1849, utilizing an ingenious mechanical setup. Fizeau's experiment was built on the principle of a rapidly rotating toothed wheel, acting as a timing mechanism. Here's how his apparatus worked. A bright beam of light was focused. This light beam was directed towards a rapidly spinning wheel with precisely cut teeth and gaps along its circumference. The light passed through one of the gaps in the rotating wheel. The light then traveled a significant distance, Fizeau used about 8.6 kilometers, to a stationary plane mirror. The mirror reflected the light back along the same path. The reflected light returned to the rotating toothed wheel. The critical insight was this: if the wheel was spinning at a certain speed, the light that passed through a gap on its outgoing journey might be blocked by an adjacent tooth on its return journey. By carefully adjusting the rotational speed of the wheel, Fizeau could make the light disappear or reappear at the observer's eye. If the wheel spun slowly, the light that went through a gap on the way out would return to the same gap on the way back and be seen. As the speed increased, the returning light would be partially obstructed by a tooth. At a specific higher speed, the returning light would be completely blocked by the next tooth, causing the light to disappear. By measuring the following parameters, Fizeau could calculate the speed of light, the distance from the toothed wheel to the distant mirror, and back, so the round-trip distance, the number of teeth on the wheel, the rotational speed of the wheel at which the light was first blocked. Knowing the number of teeth and the rotational speed, Fizeau could calculate the precise time it took for the wheel to rotate by the width of one tooth, or more precisely the time it took for the next tooth to move into the position of the previous gap. This time interval was exactly the time it took for the light to travel from the wheel to the mirror and back. Fizeau's experiment yielded a value of approximately 315,000 kilometers per second for the speed of light. While still not perfectly accurate, it was remarkably close to the true value and, more importantly, it demonstrated that the speed of light could be measured with precision in a laboratory setting without relying on astronomical observations. His method laid the foundation for subsequent terrestrial measurements, particularly those by Léon Foucault and Albert Michelson, who refined the use of rotating mirrors to achieve even greater accuracy. The contributions of Ole Rømer and Hippolyte Fizeau were monumental. Rømer's astronomical observations provided the crucial initial evidence that light travels at a finite speed, fundamentally altering our understanding of how light propagates through space. Fizeau, on the other hand, brought the measurement of light speed down to Earth, demonstrating that it could be precisely determined through ingenious mechanical setups in a laboratory. Their methods, though different, collectively illustrated the remarkable journey of scientific inquiry, from broad cosmic observations to detailed terrestrial experiments, ultimately leading to the precise definition of the speed of light we use today. These pioneers paved the way for future scientific breakthroughs, including Einstein's theory of relativity, which recognized the speed of light as a universal constant, a cornerstone of modern physics. If you found this exploration into the fascinating history of measuring the speed of light illuminating, please consider liking this article. And for more deep dives into the wonders of science and its historical pioneers, be sure to subscribe to our channel.